asking ourselves. Let's go through, really have to just go through each of these one by one, right? So the first one says that the limit as x goes to a of f of x equals 4 implies that the limit as x goes to a of f of x is equal to 4. Now that's asking us to go back to one of our right, so if we go back to our notes from the last time, or from last Friday, slight change, I'm sharing stuff, so you can see the whole window. Right, if we go back to these notes from last Friday, right, we talked about one-sided limits and their relationship between that and the general limit, right? The general limit, right, implies, right, so if the limit is x goes to c of f of x equals L, that implies both of the one-sided limits have to equal L. Right, and so that first one is going to be true. But that same statement, right, if I want to go the other direction, then I have to have both of those being true, right? And in particular, right, oh, the second one doesn't, sorry, I missed that negative sign when I was looking at it, right? The second one here, just asking, I'm going to make this bigger just to make my easier. Right. Knowing about the right-hand limit, right, doesn't really tell me anything about the left-hand limit. And we've seen example problems, right, like the limits here at 6, right? The left hand and right hand aren't necessarily the same. That problem we started off class with, right? And so that one's not going to be true. Those two aren't related. Third one, the limit is x goes to a of f of x equals 4. And I know that the left-hand limit equals 4. Well, yeah, I mean, this middle piece is actually extra information. If the limit is x goes to a of f of x equals 4, then both of those two things have to equal 4. Both the left hand and the right hand have to equal 4. So that's true, even though it's got some extra bits. Right, the limit is x goes to a equals 4. Well, yeah, that's why I said this is really kind of like an extra bit, right? Because if the general limit, right, equals that value, then both the left hand and right hand also have to equal that value. The limit is x goes to a, right, equals 4. Well, right, this is all really using that same, so far, that same statement about the connection between general limits and one-sided limits, right? And once again, if I want the one-sided limits to tell me anything about the general, they both have to have that same value, right? Otherwise, we can end up being in a situation, right, like at 6 here, right? The left hand, so, right, the limit from the left was 2, the limit from the right was 5. And that tells me nothing about then the limit as I go to 6 doesn't exist because those two are different. So if I only know about the right-hand limit and don't know anything about the left, right, I don't know anything about the general limit. And the same thing, just knowing something about the left-hand limit doesn't tell me anything about the right-hand limit. And knowing about the left hand, if I don't have any information about the right hand, right, then I don't know about the general limit. So all three of those, I only have partial information, so they can't tell me anything either about the other one-sided limit or about the limit in general. If I look at that second one from the bottom, the limit as x goes to a of f of x is 4, and the limit as x goes to a from the right is 4. Well, yeah, that's similar to this third statement here, so that's going to be true. But once again, that's like this isn't even really needed. That's extra information. It's still a true statement, but I don't really need that. This last one here is really where I need both pieces, and it's the one case where the one-sided limits can tell me about the general limit because I know that both the right-hand limit is 4 and the left hand is 4, right? And as long as I have both pieces, right, then I know that the general limit also has to be 4. Anybody else? Other questions, comments?
I have a question on a different problem.
Yep.
It was number 6.
Same section?
Yes,
Cool.
2.2.
Okay. Okay, so this asks us to guess the value of the limit if it exists by evaluating the function and at different decimal places. So let me bring out a calculator here. Over, yeah, I'm sharing that whole screen. A little bit bigger. Okay. Right, so our function cosine of 3x minus cosine of 8x over x squared, and we're trying to find the limit as we approach 0, and it gives us values to plug in. So my numerator, I'm going to put, since the numerator is the difference of two things, I'm going to put that inside of parentheses to make life a little bit nicer. So 3 times 0.2 minus cosine of 8 times 0.2, close the parenthesis for the cosine, close the parenthesis for the numerator, and then divide that by 0.2 squared. Right, so okay. So that's giving me something like 1.555. I go to 3 decimal places. Sorry, I was looking to see if the problem asks for a certain number of decimal places. It doesn't look like it does. Radians, always in radians, never in degrees. Anytime we're dealing with trig functions, you always want to be working in radians. All right, if we go to 0.1, let's turn those 0.2s into 0.1s. All right, so negative 68.71533. A very different looking number there as we got closer to 0. So far, the trend's not necessarily obvious. If I go to 0.05, so let's turn that into 0.5, 0.05. Squared. Right, so negative 367.43. I'm getting big negative numbers out so far. Times 5s into 1s. Negative 9967. Being big enough, I'm not gonna write the decimal. It doesn't look like we're getting smaller and worried about getting close to a number that way, right? This case looks like we're going off to, and honestly, this looks like we're going off to negative infinity. so far. All right, make it a little bit closer to 0. All right, negative 999,967. Yeah, and so this definitely looks like we're going off to negative infinity. Right. And I'm going to skip down to 2 rows, mostly in the interest of time. And yeah, negative a whole bunch of 9s and then 6, 7, some change. Okay, right, and so that would say this looks like negative. If I keep getting out bigger and bigger negative numbers, right, we're going off to negative infinity, right? And if we go back to the thinking about this problem, instead of doing these approximations just intuitively, right, the number on the bottom is getting closer and closer to 0, right? And I'm squaring it, so this is becoming my denominator, right, in a different color, right? This denominator here looks like it's becoming a large positive number. And in my numerator here, cosine of 3x minus cosine of 8x, this number on top looks like it's going to a kind of a constant, right? Negative constant, right? So that the cosine of 8x, when we get close to 0, is just a little bit bigger than the cosine of 3x, right? In other words, this one's just a little bit more positive than that is. And so when I take the difference, I'm going to get a negative number, right? That negative, it's negative, that constant is really another way to say the same thing. In fact, we know what the constant is because those two look like it's going to cosine of 0 minus cosine of 0. So I could be more precise instead of saying a negative constant. This is approaching 0, right, from the negative side. And so this is kind of one of those problems that we're going to need some more tools to deal with it more precisely, because if I have something that looks like it's going to 0 divided by a big positive number, like that could go to 0, that could go to a negative infinity. A lot of things can happen here. It depends upon whether or not the numerator is growing faster than the denominator, and we need some kind of tools to do that precisely. Right now, all we have are these good ways of thinking about it, both intuitively and approximations, right? My intuitive ideas here don't actually tell me a lot. The estimates that we get, though, by just plugging in values do tell us a lot more about what's going on there. Anything else? Okay, so let's then jump into section 2.3. Okay. Section 2.3 here is called limit laws, right? And limit laws are going to be a way for us to take limits of more complicated functions. Really, what we're going to do is be able to break down functions or apply, really not break down functions, but break down limits using functional properties so that all we really need to be able to rely on are this set of theorems here, right? The ones about the limit as x goes to c, right? And then our limits at infinity. And primarily we're going to focus not the limits at infinity. I mean, those are important and we will focus on them eventually. At the beginning here, we're just going to focus on how can we take kind of limits at a value that c, right? That is some actual number, right? That's not plus or minus infinity, right? Those aren't numbers, those are concepts. How can I take the limit as x goes to c of some more complicated function and break it down into a case where I can apply these simple limits here. Right? So the process of doing that is what we call our limit laws. So we're going to write down all of our limit laws in this question here. All right, so let's assume that the limit is x goes to c of f of x, and the limit is x goes to c of g of x exist. Right? If those don't exist, things can break down and some of these statements might not necessarily be true. So if the one-sided limits, right, if either f or g have issues with one-sided limits, right, some of these statements can be true sometimes they can be false. But as long as each of those individual limits exist, right, this set of limit laws here is always going to hold. Okay. First one. All right, so the first limit law is called the sum and difference law. Right, the textbook puts these kind of as two separate things, but subtraction is really just adding a negative number or a negative function, negative value. So addition and subtraction are really, in many ways, the same operation. So I'm going to write them like they're the same operation. All right, now use parentheses just to emphasize breaking things down appropriately. Right, and in calculus, we're going to use a lot of parentheses. Parentheses are going to be really good friends of ours because we're going to need to be really, really careful about how we break things down. Right, so the sum and difference law says that the limit as x goes to c of f of x plus or minus g of x is equal to the limit as x goes to c of f of x plus or minus the limit as x goes to c of g of x. Or another way of saying that is that the limit of the sum and difference is the sum and difference of the limits. Right, the second limit law is called the constant multiple law. It says that the limit is x goes to c of a constant k times a function is equal to a constant times the limit. Right, so k a constant. Right, in other words, if I have a constant times a function, I can just factor that out in front of the limit. Right, it needs to be multiplied by that whole function, so it needs to be a common factor. Right, but as long as that's the case, right, I can factor that out. Now, these two limit laws together, or these two properties here, are what are referred to as the linearity laws. And the linearity laws occur together in a lot of different places. So we're going to see them when we get to derivatives, when we get to integrals. If you're a math major or an engineering major and take linear algebra, I mean, linear algebra really is a whole the whole area of algebra that's reliant and is based upon kind of those two laws in many ways, sum and difference law and the constant multiple law. All right, but there's another collection of limit laws that kind of don't always have analogies in other parts of math, or they may operate differently, right? And so these next few that I write, we're going to have to be a little bit more careful with. They were pretty straightforward with limits, but they're not going to be so straightforward when we see some other types of operations later on this semester. So we can talk about the product law, which says that the limit as x goes to c of the product of two functions. All right, so f of x times g of x is equal to the limit as x goes to c of f of x times the limit as x goes to c of g of x. In other words, the limit of the product is the product of the limits. Talk about. Also look at quotients. Right? And so quotients are dividing, right? One function divided by another. And unlike sum and difference, even though quotients are basically like multiplication, right? Division and multiplication, pretty much the same thing. I have to be a little bit more careful here because I need to make sure that I'm not going to divide by 0. So I get that the limit of the quotient is the quotient of the limits. So the limit as x goes to c of f of x is over g of x equals the limit as x goes to c of f of x over the limit as x goes to c of g of x, right? This is when that second limit, right, the limit of g of x, right, isn't 0. If the denominator is 0, then we got a little bit more that we might have to do, right? Have to be a little bit more careful, right? And we actually just saw that in that last example, right? When we kind of try to think about what's going on here, right? My denominator was going to 0. Oh, why did I write large positive? Small positive. Let me fix that as well. Right. It was when I took reciprocals, I got large positives, but it should be a small positive. Right. Because that's going to 0, right? Limit as x goes to 0 of x squared. Well, small numbers squared, still small numbers, right? That looks like that's going to 0. Like I said, the numerator also looks like it's going to 0. And so when my denominator is going to 0, I have to be a little bit more careful, and we can get stuff that like this to where it's not quite obvious what's going on, right? And those limit laws don't directly apply. I can't just take the limit of the numerator, which is 0, and the limit, which is the denominator, is 0. Then I get 0 divided by 0. Don't know what that means, right? That can mean a whole lot of different things. For the most part, it means I need to do some more work. So as long as my denominator is not 0, I can simply just take that quotient and I'm good. When it is 0, different story. And then finally, the last one is the power and root law, right? Which says that the limit x goes to c of, I have a function to some power or root, right, that I can push the limit inside and then apply the power and root, right? And so here we have, right, p over q, right? This is a irrational number, right? In other words, right, p and q are integers. Q is not 0, right? I don't know, once again, I don't want to divide by 0 in any situation. doesn't make sense to have 0 in the denominator of an exponent. But, right, those p's are powers, right? So that, like, if I'm squaring something or cubing something, right, that's like having p equals 2 or p equals 3, right? Q values are roots when I put them in exponents, right? So, like, if this was like 1/2, right, that's 1/2 over there, right? So I can push the limit inside of a square root, right? Negative numbers are fine as well because negatives are just reciprocals, right? And so things work nicely with reciprocals, right? Just have to, once again, be a little bit careful about making sure I'm not dividing by 0. As long as that's not the case, right? Everything is good. Okay, so we got about a little over, or about 7 minutes left. Let's do an example. Try to get one that I can do relatively quickly here. 2.3. Okay, and so this is problem number 85 from your book, right? And this problem asks us to, oh, I forgot to copy that part of the problem, right? Use the limit laws to evaluate that limit, right? And so if we're going to use the limit laws to evaluate it, right, the only thing that we're allowed to rely on in terms of evaluating the limits, right, is our theorem, right? The theorem that says, put this up here, or anytime I write theorem, I'm referring to the theorem that the limit is x goes to c of a constant. Is that constant, and the limit is x goes to c of the function x is equal to c. Notice if I compare that and my limit laws, right? My limit laws on both sides of these equations still have limit signs or limit symbols, right? That limit operator can't be gotten rid of using limit laws, right? The only thing that can allow us to evaluate limits is this theorem here, right? Because it's just got a constant there and it's got the value c there, right? Aside from that, that's the only thing, that's the only way for me when I approach this problem to get rid of any limit signs is going to be to use that theorem. So I'm going to need to do some work to where that theorem is all I'm going to need. So if I want to start using my limit laws, it asks me to justify each step, right? Well, I see I'm taking the limit as x goes to -2 of the square root of something, right? That square root is exactly our power and root law. So I can write this as, put that square root on the outside, put the limit on the inside. And then I need to be careful because this limit applies to that whole function. So I say parentheses are going to be really important to us. Make sure that I'm applying that limit to the whole thing, right? If I forget the parentheses, just like my calculator, it's only applying to that x squared, right? Gotta be really careful, both in putting things in calculators or how are these limit operators being applied. Okay. Now, I'm now seeing inside of my limit, right, a polynomial x squared minus 6x plus 3. And a polynomial is the sum or difference of a bunch of terms. And so I can use the sum or difference law to separate that, right, into 3 limits. All right, so I got the limit as x goes to -2 of x squared, right, minus the limit as x goes to -2 of 6x plus the limit as x goes to -2 of the number 3. Right, now that last thing I just wrote down, I could use my theorem to simplify it. I'm going to wait until I get to the point where my theorem is all that I need before I apply that theorem. So I'm just going to kind of keep this last little limit here floating around, and then I'll apply that limit as we get there. Now, the other two limits that we still have in here, right, the theorem doesn't apply, right? This is an x squared, and I can only apply it to x. I need to use the power and root law again for that 2. And the 6x here, well, the 6 is a problem, right? But I can move that out into a front using the constant multiple law. And I'll do those separately, primarily just for sake of notes when I post these online. So here, if I use power and root law, again, I can take care of that first limit, right? Put the square on the outside. Everything else stays the same. And then use the constant multiple law to push that 6 out, right? So I have the square root. Here I've got the limit. X goes to -2, x squared minus, now I can move that 6 out, limit x goes to -2 of x plus limit x goes to -2 of 3. Right now, all three of these limits look like they're in the theorem, right? The first two limit is x goes to a constant of x, right? That's the second part of my theorem. The last one here is the limit of a constant, which is the first bit of the theorem. So now if I apply the theorem, right, this looks like the square root of, right, -2 squared minus 6 times -2 plus 3. And so that's the square root of 4 plus 12 plus 3. And that looks like then the square root of 19. Right, now that was a whole lot of work for, in the end, right? I mean, at this point here, you kind of go, all you did was plug -2 in. Why didn't we just do that at the beginning, right? And so our limit laws are a nice tool for helping us evaluate these limits, but they're not necessarily very efficient, right? They don't allow us to do things necessarily in the quickest way possible. And so part of what we're going to start looking at when we get into the next section in 2.4 is to answer that question of when can I just plug the number in and when do I need to do something else, right? So we'll see some examples next week when we continue on in this section where things start to become a problem. I mean, we've seen a number of examples already where we have things that are a problem. And sometimes the limit laws are going to be able to help us, and sometimes we're going to have to figure out, well, the limit laws are always going to be able to help us, but sometimes we'll need to be able to figure out how to do things slightly more efficiently without them, and what properties necessarily can make things go wrong. And if so, how can they go wrong, right? And that's really what 2.4 is about. We still got a while before we can get there, but I think it's good foreshadowing of what's coming up, right? You should be able now to get started on the 2.3 homework as well, right? We finished 2.2, so that it's going to be due beginning of next week, right? Once again, that's right. Kind of make sure you're doing time management well, because I'm not going to set the official due date until the actual test, right? But our formal due date really is next week, so that way you can bring those questions on Monday from the rest of 2.2. And you should also be able to start 2.3. Like I said, might not be able to get a heck of a lot done. In some sense, we've gotten a good amount of ourselves started with our limit laws, right? But there's still a lot of open-ended questions that we're going to have here in 2.3 that's going to require a little bit more. So any last-minute questions, comments, concerns, or other things from anybody? It might, the way that you just typed it, you would actually need the 1/2 inside of parentheses as well. It might take it like that. You can also see if I need to turn this to the student view thingamadoodle. So on some problems, on the MyLab, or on, oh, sorry, on My Open Math, this class doesn't, other class. Yeah, here's a good example. All right, so here's like one of the 2.3 problems about limit laws. Like when I get to this problem here, if the answer became square roots, as soon as I type in, it brings up this set of mathematical functions or operators, mathematical symbols. I would just want to use the square root button rather than the 1/2 power. Basically, if it's prompting me to use these, I should probably try to use those in my answer. I mean, if it was on a written test, you would be perfectly fine. It's when it comes to typing stuff into My Open Math. It usually only likes one or the other, not both. But since you have infinite tries and there's no penalty, just as long as you're comfortable, or well, you should be comfortable going back and forth between the two ways of writing it. You might have to try one, and then if it doesn't like it that way, try the other. Does that answer your question? Cool. Yeah, the one thing you don't want to do is put in a decimal approximation unless it tells you to, right? Decimal approximations are often all right in application, but from a mathematical sense, right, if you put in the square root of, it's like 4.6 or something. If you put in like 4.6, whatever the few decimal places are, that's going to be wrong 100% of the time unless it asks you to do a decimal approximation, only because that number is technically not the square root of 19. Square root of 19's got an infinite decimal expansion. Okay. Anybody else have any last minute stuff? I know we're a couple of minutes over, so if you needed to leave, please take off. I mean, I'll sit here and answer questions if people still have them and they want to ask them, but I don't want to hold anybody up, especially if you have a next class. Hey, have a good day too, Jordan. Yep. Yeah, I hope everybody has a wonderful weekend.